house flipping as one of my options. Excuse me. Do 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 do. Oh, why do I have all of these? Oh, my pencil bag. Can't mix pencil bags. Come on, get it together, Sarah.
Something has been so weird with our YouTube streaming.
Last week, it was YouTube that was good. Thursday.
Right, but it's saying that somehow we've been live for like a week or something, and I was like, we were not live.
All right, everybody, welcome to MaTHURSDAY. Here you can ask me anything, any math questions or anything that you want to know about, or if you need help, maybe you got a test coming up, put it in the chat. Welcome. All right, so we've got a list of questions that people have been asking about, especially systems of equations. That one comes up a lot. Happens a lot. One of my all-time favorite things is long division with polynomials. That's on the list. Let's see. Year 6 SATs, I think. Year 6 SATs. Struggling with how to work out percentages. So percentages are basically like fractions. But they're in like percent means per 100. So you're kind of looking at like what fraction of 100 would it be? So like if it's 3/5, right, and you've got something over 100, right? So 3/5 into 100, you would go like, well, okay, so 5 times 20 is 100. So 3 times 20 would be 60. So 3/5 is 60%, meaning 60 per 100. So that would be 60%. Okay. Now, yes, I know this is a very easy conversion over from 5 to 100. I get that. So if something's a little bit more difficult, right, a little bit more, I'm not even going to say difficult, just a little more complex, right? Just difficult and complex are kind of different things. So if I had something like, I don't know, 5 out of 7, right, equals something over 100. Okay, so we've got this question mark here. Okay, so you're still doing the same idea. It's still the exact same idea. You're figuring out, okay, this number times what gives me 100, right? So if this number times this equals 100, then this 100 divided by 20 gives me 5. So I can use that the same way. So to figure out 7 times what equals 100, what I can do is I can do 100 divided by 7, right? So 100 divided by 7. I didn't make this very friendly for myself, but we'll go with it, okay? So 7 into 10 goes 1. 1 times 7 is 7. Subtract that, I get 3. I bring down the 0. I get 14, so that's going to be 28, so that's going to be 20, so it's 14.2, let's say, okay? So 7 times about 14.2 gives me 100. So then 5 times 14.2 would give me this percent, okay? Easiest way to do it Easiest way to do it is if you do 5 divided by 7 times 100, that's going to give you your percent. Okay, so 5 divided by 7 times 100 is going to be the same thing as figuring out this whole fractional rate, right? So 5 divided by 7 times 100 is going to give me my percent. Okay, so I'm just going to grab this calculator. Right, so when you're using these, 5 divided by 7 is 0.71428574143. Usually you round it to like the nearest tenth, maybe. Depends on what your teacher says, right? So that would be, so 5/7, or 5 divided by 7 times 100 is going to give us 71.4%. So it's the same idea, right? So you've got 5 out of 7 is the same thing as 71.4 out of 100%, like century. So that's where percentages come from, is looking at these percents, right? All right, so that's a little brief on percent. Okay, so again, if you're just joining us, this is MaTHURSDAY. So if you have any questions, anything that you're working on or learning about in math that you have questions about, anything from basic arithmetic operations all the way through to like pre-calc concepts, right? So we can do kind of anything, whatever you need help with on math. Okay.
We got some chat. We've got quadratic systems. People asking about fractional unit rates.
Okay.
And someone separately. And also, can you do butterfly cross multiply? The divide number not used yet.
Cross multiply, butterfly cross multiply. So that would be like, yeah, so the butterfly cross multiply, that would work too. So let's go back to that 5/7, right? So 5 over 7 equals something over 100, right? If we're trying to get to percent, so you could do 5 times 100, which is 500. And then you would divide that by the one that's not used, which would be 7. And then you don't have to move the decimal or anything over, because if you do 500 divided by 7, or we do 500 divided by 7, we get 71.43, which is the same thing, right? You would get 71.4%. Yeah. And there's always so many different things that you can figure out with percentages, with fractions, with multiplying, with divide, because ultimately it is all multiplication, right? We're just multiplying by reciprocals and all these kinds of things. And, percentages are reversible. Multiplication is reversible. It's all over the place, right? Pancake mix, you're back. All right, how do I know when to have a negative for algebra? Can you tell me a little bit more about that? When to have a negative for algebra? Give me a little bit more context with that, and I can help you out. Okay. Pancake mix, something hard this time? Every time you join. But we'll sort it out. Let's put it in the chat. Okay, let's see. What else did you say? Quadratic fractional unit rates?
Let's see. Fractional unit rates was one person, and someone asked about quadratic systems.
Okay. So, fractional unit rates. So fractional unit rates, what I'm thinking is if it's, okay, so when it's a positive on one side and a negative is already on the other side. Do you mean something like 2x equals -4? Something like that, SP 5000? Where we have this positive on one side and the negative is over here? Right, well, they were asking about the negatives in algebra. Okay, so with this, if you've got 2x equals negative 4, right? So when you look at something like this, a lot of times this will come from an equation that's a little bit further along, but you'll get to this last point here, right? So what you would do is what you're looking for really is 2 times what equals negative 4, right? So when we have 2 times something is negative 4, you can think about that. So you can look at this like, okay, well, 2 times 2 is positive 4, right? But I have a negative 4. So the rule with negatives is if you are multiplying or dividing and the signs are the same, so you're multiplying or dividing 2 positives or 2 negatives, the answer is going to be positive, no matter what. If there are 2 negatives, it's positive. If it's 2 positives, it's positive. I think I said that right. Now that's only for multiplying and dividing. With adding and subtracting, it's a little bit more, that's when we get into like the number line and canceling values out. But here, if I've got 2 times what is negative 4, well, this 2 is not negative. So that means that what's in the x has to be the negative one, right? So it would be 2 times, I'm going to use this, 2 times negative 2 would give me negative 4. So that means that 2x is 2 times negative 2. So x equals negative 2. Okay. The other way you can do that is if you start with this 2x equals negative 4, right? So this way you can just kind of see it, right? But otherwise you can divide both sides by 2. Right? Because if you've got 2 times a number is negative 4, then you could have 2 times 2 is negative 4. Or negative 4 divided by 2 gives you negative 2. Okay, so just a couple different ways to do that. Okay. All right. Okay, quadratic. Are we solving quadratics? Is that what you're asking for? We've got solving quadratics and transformations with the domain. Okay, I'm going to keep a note. Okay, so domain and range are coming up pretty frequently. So domain, range, and transformations with domain and range. Ah! Ooh. Lost my little thing. Okay. Uh-oh. Hold on. Okay. Okay, so transformations with domain and range. What we really need to, well, first, you want to talk about, let's see, okay. Okay. That's a quick question. So is negative 3/4 an integer? No, it's not. An integer is a number that's a whole number, but it can be positive or negative. So 1, 2, 3, 4, 5, those are counting numbers, right? And then integers are the negative versions also. So -1, -2, -3. So 3/4 is not an integer, but it is a rational number. So a rational number is something you can write as a fraction. So 3/4, 1/5, 5/8, whatever that is, right? So that would still be a rational number, but it's not an integer, okay? Okay, scientific notation. I'm just keeping a quick little list over here. Okay, so domain and range. When you're looking at, where are my? Okay, a sardine bag with all my dry erase boards. Okay. Okay. All right, domain and range are talking about sort of like the limits or like the areas of the domain and range are all with the x and the y values. Okay, so the domain of a function or of an equation or a line or whatever it is, right? The domain is all the x values. The range is all the y values, right? So if you are like increasing the domain, right, you would be increasing the x values. If you're increasing the range, you would be increasing the y values. Or decreasing the range would be decreasing the y value. So thinking about how you're shifting that, right? Just for translations and things like that. So if you have something like a parabola like this, right? Okay, let's pretend it's actually symmetrical. Let me see. Let me draw it a little more symmetrical. 1, 2, 3, 4, 1, 2, 3, 4. Let's go it like that, okay? So it's here, okay? So the domain, these keep going. There are no limits. There's no boundaries. So this is going to keep going forever and ever and ever and ever. So it is going to pass through every single x value. So my domain would be all real numbers for my x value, okay? But my range is only going to be my y values that are over or equal to, right? Greater than or equal to +2. That would be my range, right? So my range is all the y values. My domain is all the x values. So again, it just depends on what you see, right? So you might see something like this, right? Okay. So this line is not going to have any positive x values or any positive y values, right? It's only going to be negatives, okay? It's only going to be negative x values and negative y values. So these are where you have these limits, right? So if you have something like a domain of -7 is less than x is less than 9, so it depends on what kind of function you have, right? So pancake mix, are you talking about piecewise functions or what are you talking about? Because your domain of -7 is less than x is less than 9. So 1, 2, 3, 4, 5, 6, 7. So you've got from there 1, 2, 3, 4, 5, 6, 7, 8, 9 is here, right? So your x values are only going to be in between here, okay? Now, if you're talking about a piecewise function, right? If that's the limit, so let's say it's, I don't know, if it's a piecewise function. So piecewise functions are really interesting because they're where you have a lot of different equations or different functions, but it's like it's only one particular function for that area. So if you had like two functions that were going on, where you have f of x as a function, right? So f of x is 2x minus 1 if, let's see, -7 is less than x is less than 9, right? And then maybe you have like f of x is 4, sure, when x is less than -7, less than or equal to, we'll say. Okay, so if we have that, that's getting into a piecewise function, which means that when the x value is between -7 and 9, we're going to follow this line. Okay, and then here, if x is less than or equal to -7, we're going to follow this line, which is just y equals 4. Okay, so let's graph this, right? So we're going to graph this piecewise function here. Oh, it's kind of hard to see, huh? Okay, so I'm just going to look at these. Okay, so 2x minus 1. So this is a really good refresher on graphing linear equations also. So 2x minus 1. So this is my y-intercept, right? Now somebody earlier was asking, like, how do I find the y-intercept, right? So this is my y-intercept. The intercept is just where it crosses the y-axis. The x-intercept is where it crosses the x-axis. So when it's crossing the y-axis, that means that x is 0. If it's crossing the x-axis, that means y is 0, okay? So 2x minus 1, so that means that my y-intercept is negative 1, so it's down here. Then my slope is 2, so that's going to be up 2 over 1. Up 2 over 1, up 2 over 1, up 2 over 1, okay? Down 2, left 1. It's going to be one line that goes all the way through, right? I'm going to grab my straight edge, because we want to be as precise as we can be, right? Okay. So this is my line of 2x minus 1. Okay. But this is going like the whole way through, right? Oh, you know what? 1, 2, 3, 4, 5, 6, 7. Shoot. I've made a mistake because I set these limits here for the domain. I set these limits to where, like, you're not going to see them on this graph. So let me change these just a little bit, just because I want to be able to show you what it does. Okay, so we'll do we'll change our limits to, like, when x is between negative 2 and positive 5. Okay, and then this is when x is less than or equal to negative 2. Okay, so there, I didn't really change anything about what we would do so far. It's just changing the limits purely so you guys can see this, okay? All right, so 2x minus 1, but your function is only going to follow 2x minus 1 when the x value is between negative 2 and 5. So when x is greater than negative 2, so that means that here we've got where the x value is negative 2, and where that is on the line is right here. Now what I'm going to do is, this line does keep going, usually, but I've set a little limit on it, right? I've set a boundary. So actually, this line is only going to go until the x value is negative 2. Okay, and it might be kind of hard to see, but that is an open circle. The reason it's an open circle is because it doesn't include negative 2. Okay, so if this had the little line under it that meant or equal to, that would be fine, right? Like that one. Okay, and then x, and then so it goes from negative 2 and it just stops at 5. So 1, 2, 3, 4, 5. Ooh, we just made it. Okay. So that right there, that is my first piece of my function, okay, that it's 2x minus 1 when negative 2 is less than x is less than 5. Okay, now, if this were less than or equal to 5, I would do this. I would fill that in because it includes that value. Okay. Now my other piece to this piecewise function is that y is going to be 4 when x is less than or equal to negative 2. Well, y equals 4 is just a horizontal line. Okay, because it's the whole line, everything, like no matter what the x value is, y is 4. X is 2, y is 4. X is negative 5, y is 4. X is 10,452, y is 4. That's it. Okay, so it's always going to be a horizontal line right here. 1, 2, 3, 4. It would be right here. Okay, so it would be a horizontal line all the way through. Now, we've got that limit, right? So we've got that limit. It's only going to be there when x is less than or equal to negative 2. So when x is negative 2, I'm going to go 1, 2, 3, 4. I'm going to put in a filled in circle. And I'm really exaggerating these just so you guys can see, right? These dots and everything, I'm exaggerating them so you can see them, right? So from there to any x value that's less than or equal to -2, that's where that y value is going to be, or that y equals 4. Okay, so it's going to go like that. And this one, because there's no lower limit, it's going to keep on going. Okay. So this data set here, this piecewise function is not a continuous function, because a continuous piecewise function would be if you could follow the line without lifting up your pencil. Okay, but in this case, we go here, and then we have to go, we have to do this big jump, and then we continue on, right? And then it ends. Okay. Oh, I got a galaxy. That's something big, isn't it? I think so. I still don't quite know what all these things are, but thank you for the galaxy. That's exciting. All right, so we've got these. Okay, so this is what's called a piecewise function. So again, this is kind of dealing with like your domain and your range. So hopefully that really, how would you get a point out of a continuous one? Do you mean like if you had something like f of 3? If you're trying to figure out what f of 3 would be? So a lot of times these are kind of the follow-up questions to these, is like, what is f of 3? So in that case, you've got this function notation. So that means it's asking you, what would you get, like what would your f of x be, or what would the y value be if x is 3? So we look at these different kind of limitations, and we see, all right, so we've got f of 3, and then we would do f of 3 is here, so then f of 3 would be on this line, so it would be 2 times 3 minus 1, so that would be 5, right? So f of 3 would be 5. Okay, now if I had f of -6, well, -6 is less than or equal to -2, so I've got 4. Remember, it doesn't matter what x is, y is always 4. Okay? So it doesn't matter what x is, except when x is less than or equal to -2, right? Okay. All right. Oh, sigma.
That's Rhodey.
Rhodey. Ugh. Sigma. It's the bane of my existence right now. Every time I say sigma, I'm like, yep, standard deviation is sigma. Got it. How about when you get f of x? So, I just erased all the things, but I remember we had like f of x is 2x minus 1. So do you mean like if I asked you what f of x minus 4 is? So this, with the function notation is, it feels really confusing, but I promise you it's not. It's literally just whatever is in these parentheses, that's what you put in here for x. So f of x minus 4, that is what goes into the parentheses. So, or that's what goes in for the x. So you would have 2 times x minus 4 minus 1. So that would be 2 times x, which is 2x. 2 times -4, which is -8, minus 1. So it's 2x minus 9. That's what it would be. Okay. So one of your other questions, I think, was, where are all my boards? Here they are. Losing all my boards. I don't know what's going on. So if you had time a leak. Okay, so if you have something like, so we'll stick with this f of x. Am I doing my PhD now? No, I'm not doing my PhD. Nope. Just a math teacher, just doing math at my dining room table. This is literally my dining room table that I'm sitting at. Because, you know, that's where a lot of math gets done. So, welcome to my house. So if I have anything in front of the f of x, right? So we're going to stick with this f of x equals 2x minus 1, okay? So if I have like 3 plus f of 2, right? If I did this, and I know that f of x is still 2x minus 1, I would figure out, I would do f of 2, right? And f of 2 is going to be 2 times 2 minus 1, because again, whatever's in the parentheses is just what I replace that x with, okay? So 2 times 2 minus 1, but I've still got this 3 plus, right? So we've got 4 minus 1 is 3. So we've got 3 plus 3, which is 6, okay? So if there were, oh man, derivatives. Oh boy, that's exciting. We might have to wait until next week to get into that. Yikes. Or you might have to give me a few minutes to double check some things. Okay, so here with this f of 2, you want to make sure that you figure out what this is, because f of 2 in this context does actually stand for a number, right? It does actually mean a number. So you have to solve this to get this value first, then you can do everything else. So even if it were something like, 3 plus 1/3 of f of 5. That should work. Okay. So again, f of 5 is representing a value, right? So that's sort of like a grouping symbol. I want to make sure that I get the f of 5 first, right? So I'm still using that f of x equals 2x minus 1. Okay. So if f of x equals 2x minus 1, so then f of 5, is going to give me 2 times 5 minus 1, which is 10 minus 1, which is 9. So this f of 5 is 9. So now what I'm looking at is 3 plus 1/3 times 9, right? No, fractions are the best. Fractions are no reason to give up on math. So 1/3 of 9 is 3. So we have 3 plus 3, which is 6. Yay! Okay. Fractions are so much easier than decimals. They really are. I know you guys don't agree all the time, but I say it all the time. Fractions are your friends. Okay? They make it a lot easier. Multiplying by decimals is tricky because you have to keep track of the decimal and all that kind of stuff. But if you just make them fractions, it's a beautiful thing. You just multiply straight across, then simplify. Done. Okay? That's why you're doing data science next year. Whew, data science, you're going to be doing a lot of calculators. It's fun. I just finished doing the whole statistics unit with my students while they're taking a test on Monday. Okay, let's see. Data science is a lot of pre-calc. I think you would do it. Okay, so derivatives. Oh my God. Derivatives, I am going to need to brush up on derivatives. You need derivatives? Oh my gosh. Do you have to have it tonight? Tonight? Can it be next week? It's now. You all have a test tomorrow, I'm guessing. Okay, your homework. Can you type in? They're really hard to type in. Okay, let me see what I can do. So got another question here for domain and range. And keep, change, flip. We'll go into keep, change, flip a little bit. Ooh, Mr. B. Oh man. See, calculus. Oh, calculus was it. AP Classroom simplified it weird. Okay, let me see what it might all come back to me. Hold on. Okay, so keep, change, flip. There is a reason why keep, change, flip actually works, is because okay, so D over all right, so keep, change, flip. If we do like 1/3, guys, I will do. Man, you are all. We got a bunch of calculus people on here tonight. My goodness gracious. I promise I will brush up. I will brush up on my calculus stuff. Oh my God. Yeah, I will brush up on derivatives. Elimination. Yikes. I assume that's supposed to be elimination. Okay. Oh, keep, change, flip. Okay, so 1/3 divided by 2/5. Okay, so when we're dividing fractions, okay, and I know you calculus people, you might tune out, but I promise you this does come in handy. Okay, so if we did 1/3 divided by 2/5, okay, with keep, change, flip, you would keep the first one, you would change the sign, and you would flip the last one, right? So you would keep this one, change this to multiplication, and flip this. The reason for that is because, and this is where it branches over into like a pre-calculus kind of concept. So really, I mean, stuff that you learn now, oh, and I'll do long division of polynomials too, really does come up over and over and over. So in order to kind of like figure out why that keep, change, flip works, so we're gonna do keep, change, flip. And then you're multiplying straight across and you get 5/6, okay? Okay, so there's that. So now we're gonna get into the why behind keep, change, flip. So we have 1/3. I'm gonna write this as a complex fraction, okay? It just means a fraction over a fraction. Because the division symbol, remember, is a fraction bar, okay? So we have 1/3 divided, nope, I'm gonna shift this over a little bit. Turn it this way, okay. I have 1/3 divided by 2/5, okay? The first thing I want to do is I want to get rid of that fraction in the bottom because that is ugly, right? So we've got 2/5 down here. So I want to get rid of that fraction. So to get rid of that fraction, we can do the inverse, right? We can flip it and not the inverse, the reciprocal. You guys are messing me up with all your calculus things, okay? So we're gonna flip it to multiply by the reciprocal, because if I multiply by the reciprocal, it's going to become 1 on the bottom, right? Now, whatever I do on the bottom, I have to do to the top. So this becomes times 5/2 also, right? Because I have to keep it even, right? I have to do everything on the bottom that I do on the top. So 2 times 5 is 10. 5 times 2 is 10. 10/10 becomes 1. So now I've got 1 on the bottom. These are canceling out. right? So this becomes 1/3 times 5 over 2 over 1, which is what you get when you do keep, change, flip. Look at that. So you keep, you change, you flip. Okay. Okay. So that's where keep, change, flip comes from. But it's just an extra, it's just a kind of little shortcut, right? It's not a trick. It's not anything, sneaky. It's just a shortcut, right? So it's not, these aren't tricks. They're just shortcuts. That's all it is. Okay. All right, so scientific notation. Ugh. I'm not a big fan of scientific notation. I don't really love it. I guess I understand why we do it. I guess. But it's same with like sig figs. Ugh. I think it's all left over from being like a biochemistry major that I'm just like kind of with sig figs and all of that kind of stuff and scientific notation. It's a little bit tricky for me because it is decimals. Because decimals, they're really hard. Okay. So scientific notation is a way, it's sort of like a shorthand way of writing out really, really big numbers or really, really small numbers. And the way we do this is through using like times 10 to the some power. Okay, so using those because every time you multiply by 10 or by a power of 10, you're moving the decimal around, right? So if I have 1.3 times 10 to the 6th, okay? That means I'm going to be moving the decimal to the right because this is positive, right? 10 to the 6th is a really big number, right? That's 1,000,000, okay? So 10 to the 6th is going to be a very large number. So what I would do is I would start with the 1 and the 3, and then I move the decimal from where it is to the right 6 times. 1, 2, 3, 4, 5, 6. And that's where it ends. And then you're going to add in the zeros. Okay? If we did 1.3 times 10 to the negative 6. 1.3 times 10 to the negative 6, right? Now, since it's a negative power, that's going to go to the left because this is 1 over 1,000,000. Okay, so I'm going to start over here because I know where I'm going. So I'm going to go 1, 3 here, and I'm going to start there, and I'm going to go to the left 6 spots. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So that is what that 1.3 times 10 to the negative 6 is. Now, when you're multiplying and dividing these, what you can do is you can sort of separate those out, like the 10 to the negative 6 and the 1.3. Excuse me. So if you did 1.3 times 10 to the 4th times 2.1 times 10 to the 3rd, okay? These are all multiplication, right? It's all multiplication. So, commutative property, I can do it in whatever order I want to, right? So I'm going to take these two numbers, and I'm going to take 1.3 times 2.1, and then I'm going to multiply 10 to the 4th times 10 to the 3rd, okay? And I'm just going to put in some parentheses here because these are sort of two separate parts of this problem, right? Because I want it to end up being in that format where I've got the leading number, which is between 1 and 10, okay? It's greater than 1, less than 10, okay? And then this is the 10 with the exponents, okay? So I'm going to do 1.3 times 2.1. I'm just going to use my calculator for this. 2.1 is 2.73. Yes, I know that that would be different sig figs, but I'm not worried about sig figs right now. So then 10 to the fourth times 10 to the third, when you're multiplying these exponents together, this is like multiplying 10, or I'm sorry, this is like multiplying 4 tens times 3 tens. So how many tens total? 7. So this is going to be times 10 to the 7th power. So that would be our answer. Ta-da! Okay. All right. Let me see. Oh, the long division of polynomials, right? I love doing that. Okay. All right, long division of polynomials. Let me do a... Should I just make one up and take the chance it's not going to divide evenly, but then we can talk about remainders. Yeah, we'll do that. Okay. I need help with turning tables to y equals mx plus b. Okay. All right, so I can do a little, so I'm okay edits. I'm gonna do, yeah, we can do, let's do y equals mx plus b in the, from the tables, because that's a really good thing. And then I'll do long division of polynomials, sorry. Those of you who are waiting around for it, I know. You're waiting around with bated breath, okay? Okay, so when you have a table, an x and y table, right? So x and y, and you'll usually get like 3 or 4 different values, right? So maybe you have like -2 and 0 and 4 and 5. Let's go with that, right? So hold on, let me. Okay. All right, so I'm gonna do, if x is -2, y is -5, y is 1. I'm gonna change these values, sorry, because what I've done is I've made it to where it's not gonna show up. Okay, so 1 would be 4, 2 would be 7. Okay, so we've got these values, right? And we're gonna look at all of these values and how they go. And what the first thing we're gonna do is, even if you don't know anything else about the line, right, or the values or anything, you can always graph some points. Okay, so this is something that I even tell like pre-calculus students that I'm tutoring and things like that, is that no matter what the line really looks like, you can always figure out, at least getting a general idea of whether it's a straight line or if it might curve or something like that, by just making a table of values. This is why this is the first thing that you kind of learn when you're graphing lines, is because this table of values will last through your entire math career. You can always graph a line using a table of values, okay? So we've got our values here, so I'm gonna start plotting them, right? So the horizontal axis is the x, vertical is the y, okay? So the first thing we do, and this relationship, that's what this is this -2 and -5, this is a relationship between the x and y, okay? Now the linear equation, the y equals mx plus b, is the mathematical relationship between x and y that's going to give you these values, okay? So the line is the relationship between x and y that give you these values. So sometimes you start with the equation, sometimes you start with the points, right? But it's all the same relationship that we're trying to figure out, right? So we've got, I'm gonna go x and y. So I need to, like, you hear about this all the time, where you have to walk out to the elevator before you can go up or down. It's a really good analogy, I like it. So -2, -5. So that means when x is -2, y is -5. So this is positive x, negative x, positive y, negative y. So -2, -5. So that's going to be right here. Okay, x is -2, y is -5, and where they intersect is right there. Okay, 0, when x is 0, you don't move from there. It's just right on the y-axis. So then it's 1. Okay, and already we can see kind of where our line's going to go. Okay, now we always want to plot a few different points just to make sure that it's a straight line, right? So we have 1 and 4. So we go out to 1, and then we go up 4. There we go. And we go out to 2, and then we go up 7, which is here. So now you can see that that line is really taking shape, right? So these are just the 4 points that I've been given, right? But in reality, all of these points are part of the same relationship. Okay, even all the in-between points. Okay, even all the in-between points. So this line is so many little individual points that it just looks solid, right? It's an infinite number of points. Okay? So the relationship for this, there's 2 parts of the relationship. And again, that relationship is called slope-intercept form. That one that you wrote down was y equals mx plus b. So y equals mx plus b. Okay. The b value is the y-intercept. That is where the line crosses the y-axis. Okay. The m is the slope. The slope is like kind of like the angle of the line, like how much, sort of if you think about like stairs and like putting a ramp over it, right? So the slope is the ramp, but you calculate it by figuring out like the stair steps. So the change in vertical, horizontal, okay? So we also talk about the slope being rise over run, but it's like how much are you changing vertically and how much are you changing horizontally, okay? So between 2 points, we can figure this out, right? So right here, between 1 and 4, goes up by 3, right? That's kind of hard to see. So the change in y is 3. The change in x is 1, okay? And I can see that over here between these 2 points, right? I'm going up 3 over 1, up 3 over 1. So my slope is up 3 over 1. So my slope for this line between these 2 points, I'm going up 3 over 1. So my slope is 3, and it's positive. Okay, so it's positive because it's going like uphill left to right. My y-intercept, now in this case, I can just see, and I actually know that my y-intercept is 1 because x is going to always equal 0 where it crosses the y-axis. So 1 is my y-intercept. So that would be my b value. Okay. So my slope-intercept equation, this time I just plug them in, right? So I get y equals 3x plus 1. So that's going to be my equation for the relationship that I'm showing right here. And it's the same relationship that's right here. Okay? It's pretty cool that it's all the same thing, like on these, like in these different ways of kind of like showing this different relationship between the x and the y, right? Okay. All right. Yeah, I hope that helps. Okay, let's see. How to divide fractions. We did just talk about fractions. Let's see. Okay. Lopez, what are you crying about? The derivatives thing, guys, I'm gonna need to like do a serious review of that. Let me see. Okay. Yeah, the D. I mean, so they are just formulas. Seriously, you guys are coming at me with the pre-calc stuff, huh? Well, not pre-calc even. It's like calculus stuff. Okay, so hi, friend. What are we doing? You know what? I'm going to go to the... guys, I don't think... I will put the calculus things, like the tangent functions and all of that, on the list for next week, but that's not something I feel super confident in, so I don't want to tell you something that's wrong, but I will go through and I will do some review on that, and I'll add it for the list next week, okay? I promise. Okay. So let's do long division of polynomials. That'll help some people in more advanced math classes. Okay. So if I have something like, for example, if I'm going to do like x, let's do 2x to the third plus 4x squared minus x plus 10. What's the name of the course? Just curious. Probably the Lopez. Okay. So let's see. So we've got this, and I'm going to divide it. Ooh, I don't know why I wrote it out like this. Divided by x plus 5. Sure. Okay. So what this is I'm looking. It's just like if I were doing long division of just integers or numbers or something like that, right? I'm trying to do this divided by this. So what I'm trying to figure out is what can I multiply x plus 5 times to get this, okay? So let's see if it works. Now, what I like to do is when I'm teaching my students this, I like to do a little refresher on just basic long division, right? So if I have like 148 divided by 9, right? So I'm going to look at this and I'm going to say, okay, 9 into 1, no. 9 into 14, it goes in one time. I'm going to do 1 times 9, which is 9. Subtract, I get 5. Bring down the 8, 58. 9 into 58, not evenly, but I can get to 6. So that's 54, right? So I have 4. And then this is where I always talk about remainders, right? So the remainder, if you wrote this out as an equation, right, or as like a fraction, right, it would be 16 and 4 out of 148, okay? So that is what it would be, right? And you can prove that. I always try to prove that with my students. If you do 4 divided by 148, you get 0.027, 027, 027. So if I do 148 divided by 9, I get 16.44444444. What happened with that? I must have done something. Oh, what did I do? What did I do? Oh, I typed it in wrong. Okay. So when we do this review, right, then we can go through and we can start actually like dividing. Oh my God, I just erased my whole polynomial. Oh no. Okay, I'm going to have to try to remember what I had written. Okay, so let's do 2x to the third plus 4x squared.
Yeah, I have it right here.
Oh,
2x.
thank you, Renee. I get to see my little baby socks. Their feet, I can't believe their feet were ever this little. Well, now they're huge, but I keep my baby socks so then I can use erasers and see them and enjoy the little teeny tiny socks. Okay, what was it?
2x cubed.
Yep.
Plus 4x squared.
Okay.
Minus x.
Plus 10.
Divided.
Uh-huh.
Parentheses x plus 5.
X plus 5. Okay. All right, so we're going to see what we can divide by. Okay. Oh, so cute. Okay. So what I'm going to do is it's the same process as doing division, like long division with numbers. So this x plus 5, what I'm going to do is I'm going to just be looking at this term by term. So I'm going to take a look at this x, and I'm really just going to focus on this x and what I need to multiply by. Okay? So x times what equals 2x cubed? Well, x times 2x squared would give me 2x cubed. So I'm going to put a 2x squared over here. I'm just going to shift over because it kind of lines up with the squared, right? So now that plus 5 is just going to go along for the right. So the same idea as just regular long division, right, with numbers. I do this times this, and I write it down here and subtract, okay? So I'm going to do the exact same thing. So 2x squared times x plus 5 gives me 2x cubed plus 10x squared. Because 2x squared times 5 is the 10x squared, and I subtract. So the 2x cubed minus 2x cubed, they go away. 4x squared minus 10x squared is going to give me negative 6x squared. Okay. Okay. I just realized what I did wrong on that. Anyway, okay, so x times what gives me negative 6x squared? Well, x times negative 6x would give me negative 6x squared, so negative 6x. So negative 6x times x is negative 6x squared. I bring down my minus x, and I have negative 6x times 5. That's going to give me minus 30x. Ugh, these numbers are getting real ugly, guys. This is what happens when you just make things up on the fly. Okay, so negative 6x squared minus negative 6x squared cancels out. Negative x minus negative 30x is going to give me 29x. All right, we're back into the positives. Right, so x times what gives me 29x? I'm going to do plus 29. So I bring down the 10. 29 times x plus 5, so I get 29x. And 29 times 5, I'm going to have to use my calculator for that. 145. So I'm going to subtract. So I've got this cancels out. And now I've got a remainder of negative 135. Now I realized what I had done. It's been a long day. So this remainder, I just thought about it backwards when I was doing that long division example. This remainder goes over this. Okay? So this remainder goes over this. So what's left over is going to be out of this original thing. So I'm going to move this down here. So what this becomes is this is my remainder. So this 2x squared minus 6x plus 29. That is going to be my solution, but it's going to be 2x squared minus 6x plus 29 plus my remainder, which is negative 135 over x plus 5. Okay? She's not pretty, but she'll do, right? She's not pretty, but multiply it by x plus 5, and you are going to get this big 4-term polynomial, okay? And that is long division of polynomials. Like, yes, there's synthetic division, which is very fun too. But this, oh, I love it. This is so satisfying to look at. I love it. I love it. All right. So it is 9:02. Does anybody have any last minute questions? I know I kind of couldn't really help the calculus students, but you know, can't spring derivatives on somebody last minute. I'm sorry. But next week I'll get into a little bit more of like derivatives and tangents and stuff like that. But algebra 2 is really my jam. Algebra 2, trig, getting into some pre-calc. Those are what I really enjoy. Sorry. But I will get into some calculus stuff next week as best as I can. Okay? All right, does anybody have any last minute questions, last minute requests, or anything like that? No? Okay. Well, thank you for joining. This has been a great MaTHURSDAY. And if you need micro tutoring, you can check out my Cameo, or if you want to schedule one-on-one online tutoring, or in person if you're in Southeast Michigan. Those are all options. So click the link and do the stuff.